Welcome to this live stream. I'm delighted today to be back with Scott. How are you doing, Professor Scott?
Great, thanks, Sabur.
It's very nice to have you back. And I wanted to share my screen to show a paper that you published that I didn't actually know you published this. I just randomly came
No,
across it. So this is a paper that you've published with the Royal Society, Homeostasis as a fundamental principle for a coherent theory of brains. And before we get into this paper, we're going to be discussing this in some detail. I just wanted to highlight to the viewers the history of the Royal Society. Interestingly enough, it goes back to Descartes and Spinoza. And before them, the Royal Society was known by the Invisible College. That was the term that people referred to it as. And in the sort of correspondence or the narratives between Spinoza and Descartes, there was actually a discussion of the same thing that Scott and Noble and others are alluding to today, which is holism versus reductionism. Descartes obviously being a reductionist, and Spinoza, being a holistic thinker and accepting purpose. And in Descartes' writings, we see, as Noble points out in his book, Living Systems, that you see the preliminary sort of idea of the central dogma. You find that with Descartes referring to the idea that if he knew all of the contents of the semen, he could predict the future behavior of the organism. So you see the sort of reductionist camp, setting its flag, in the 17th century. And then the Royal Society obviously is where Charles Darwin published in 1858. He met together with the society. He proposed his idea alongside Alfred Russel Wallace of the theory of natural selection. And then obviously the year later, he published his book. So the Royal Society is the oldest scientific society in the world and is quite prestigious. So the paper we're going to be going over today has been accepted by them. And obviously that means it's been peer reviewed. And so, I mean, when I hear things like, the third way thinkers are involved in pseudoscience, or, all these types of things, then it's very hard to, match that to, publications coming out in the Royal Society or even meetings that were held like those that were held in 2016. What are your thoughts on this, Scott?
on the paper, let me give you a little bit of a history about it. It's actually been published for a few years now. I think the publication date was 2019, and it was part of a conference at the Janelli Institute, which is a research institute that's supported by the Howard Hughes Medical Institute. Okay, and the conference was organized to look at different models of the structure of brains. I mean, we all think we know what brains are, and organisms have brains, but of course there are some important subsidiary questions to that, namely, well, if brains evolved, what did they evolve from? How did they evolve? Some of this you can answer just by looking at comparative anatomy and comparative biology of brains of different organisms. But our conception of brains focus on this idea of brains as part of a central nervous system. That is, you have a brain, you have a spinal cord, you have that combined with a peripheral nervous system that is the sensors of the eye and the fingers and all that sort of thing. The conference was organized in part because there's a lot of interest in looking at brains as something else. And the specific focus of this conference was on so-called swarm intelligence. And, this comes from our studies of social insects and those kinds of things. Just how is it that groups of social insects can form what seems to be a coherent organism-like assemblage of creatures, and we've known this for a few centuries now that exists. But it's become a matter of some interest to neurobiologists because with the advent of very simple robots and things like this, there's an interest in the robotics community to be able to organize swarms of robots to do interesting things, intelligent things. And one of my sets of collaborators that I worked with during my work on termite mounds was a group that was interested in just this very thing. They were a robotics group trying to develop algorithms for swarm intelligence, basically, and so that was the origins of that conference. Now, if you take the view that that brains are, coherent, compact things that are contained within organisms, how is it that you translate that conception of a brain into something like a swarm of social insects? Or another interesting focus is what happens in slime molds, when they gather together and they form a fruiting body. The kind of interesting phrase that's attached to that kind of thing, that is the kind of intelligence that you see in slime mold colonies, is that brains can be fluid. That is, they can take various forms. They don't have to exist as a coherent organ that is the case in regular organisms. And this paper that you showed of mine was trying to build upon that and say that, okay, well, you have organs that are brains that are organs. This is the common case with organisms, ranging from vertebrates to insects to whatnot. And then you have the liquid brains, as it's so called, that you find in slime molds. And the work that we had been doing on termite colonies was looking at this ability of swarms of termites to do coherent things. And of course, this was a longstanding tradition in the biology of social insects. So I said that, well, all right, you have solid brains, you have liquid brains, but termite colonies are more fluid brains. That is, they change their interactions with time. They change their configuration, fluidly, and so forth. And so that paper was basically building on the work that we had been doing on social insects to develop to make the case that there was such a thing as a fluid brain in addition to liquid brains as slime molds and solid brains that you get in organisms. And this kind of intermediate kind of superorganism type of brain that consisted of a bunch of organisms that had themselves central nervous systems, but they interacted in such a way that was very fluid and very adaptable to conditions. And so that was the origin of that paper and what the conference that it contributed to was all about. And when you propose that there are these different kinds of brains out there, ranging from liquid to solid, you have to ask yourself a deep question, namely, just what is it that's a brain? Is there some principle that unifies liquid brains, fluid brains, and solid brains all together into some kind of a coherent way to define brains? Because when you look at the evolution of brains and organisms, you get all kinds of interesting intermediate things. So, for example, in very primitive organisms like sea anemones or hydras, you don't really have a central nervous system. You have a nerve network that permeates through the body of the organism, but it's not quite a central nervous system. It's nevertheless this kind of network of dispersed nerve cells that communicate with one another. And so, what is it that drives the evolution of solid brains from say the nerve networks of the coelenterate, as the hydras and the sea anemones are called, and what is it that leads to the evolution of the neural networks from dissociated groups of cells or little organisms or what have you that had to have gone into the origin of the nerve network of hydras and those kinds of creatures. So that's a very broad outline of where the paper came from and what the motivation was behind it.
Yeah, thank you for that comprehensive introduction. What I love about this paper is that there's actually loads of segues for other researchers to develop this further, because it is a revolutionary paradigm. The first question I want to ask you is about the conceptual framework. Can you elaborate on the distinction between viewing brains as computation engines versus cognitive systems? How does each perspective influence our understanding of the concept of intelligence?
Yeah, I outline really two different ways of thinking about brains, and one I call the cybernetic model. I don't know if I'm original with that, but nevertheless, that's what it is. And this has its origins pre World War II. It was motivated by a very brilliant mathematician, Norbert Wiener, who was at MIT, and he was very interested in the behavior of organisms. He was a big a devotee of Claude Bernard, who I think we've spoken about in some of our previous times together, and homeostasis. And Wiener was very impressed by the ability of living things to self-correct, to track things and to not go off into extremes of behavior. And the elements of cybernetics actually were laid down by Norbert Wiener, and his basic idea was that you can get self-correcting machines basically by treating them as computation machines. He's a brilliant man, and the most elementary connection of that with Claude Bernard's work was this notion of self-correction that Wiener treated homeostasis as. And we've spoken about homeostasis several times already. And so, he said, well, you can make a machine to be self-correcting, and the most basic one is something called a negative feedback system, where perturbations are met with work to oppose the perturbation. And so a thermostat is the classic example of this. If you have a room that gets too warm, then you turn on the air conditioner until it gets back to some kind of set temperature. And if it's too cold, you turn on the heater, that kind of thing. And that was really the most elementary aspect of Norbert Wiener's work. He went on to build a course on Alan Turing's idea of there being a universal computing machine and those kinds of issues. But it was all related to building circuits and building machines that could do this kind of thing. And Claude Bernard's basically holistic conception of homeostasis, namely that it's a fundamental property of organisms and that mechanisms follow from that fundamental property. The work of Norbert Wiener actually turned that on its head. Now, you could speak of you could speak of homeostasis as being the outcome of a mechanism of these computing machines that you could build, basically, as long as you understood the algorithms that controlled them. And that cybernetic conception of intelligence has dominated our thinking on what brains are and these kinds of things. And just to give you an example of how thoroughly this cybernetic conception has dominated our thinking on brains, the fundamental theory of the synapse, the junction between two nerve cells, or between a nerve cell and a muscle or some other kind of cell, where a nerve cell activates, sends a message to the cell it's connected to, and then that produces a response. You can build all kinds of wonderful things from treating that interface as a so-called logic gate. You can have multiple inputs that either do produce an input or don't produce an input, or you have multiple inputs feeding off one another. And it all boils down to basically this notion that the nerve synapse, which is the fundamental means of communication within brains, is actually a kind of a logic gate. And just like you have in a computer, you can conceivably, if you know all the connections, the algorithms and whatnot, you can build a machine that can actually think. And of course, this is partly the basis of our current infatuation with artificial intelligence, and that's been a dominant theme in robotics and neurobiology, and that's where the collaboration with robotic scientists that came onto the project to work with me. That's where their motivation was. You can build a little very simple computer that exists in a little robot, and these robots can be very, very simple, and nevertheless you can get if you can build 1,000 of these quite cheaply, which you can, and you know how they interact, and you can develop the algorithms, you can develop a kind of swarm cognition, if you will, or swarm action, and so that's basically the cybernetic conception of brain function. And from the biologist side, that's been a very attractive metaphor. So if you look at the explanations from biologists for how swarms of social insects, for example, interact and do coherent things, then it boils down to basically treating the different components of a social insect colony, the individual insects, basically as these kind of cybernetic logic gates, and that you can understand the theory, or you can understand the behavior of these swarms if you understand the algorithms and how those connect to the responses and so forth. And we did some of that work. We one of our interests was to understand how the behavior of termites produces mounds of a particular morphology, and so we did some work on that, and there's some interesting things there. So that's the cybernetic conception. If I can just now switch perspective a little bit, there are some aspects of brain organization, and now I'm talking about brains like in our own heads, that don't really fit in with the cybernetic conception of what brains are. And one of the interesting aspects of that, or one of the interesting examples of that, is the diversity of neurotransmitters and the receptors for neurotransmitters. When you have a synapse, the connection basically is a chemical connection where the nerve cell releases a neurotransmitter that's then sensed by a receptor on the receiving side, and this produces some kind of action. All right. And so if you had cells acting as, or synapses acting as logic gates, you would expect maybe one neurotransmitter and receptor for an AND gate, another one for an OR gate. I hope I'm not getting too technical here, but another one for an XOR gate, an XAND gate. You can look up these terms, but the basic idea is these logic gates produce a specific response to a particular stimulus. And as I said, if you look at the different possible kinds of logic gates that there are, you would expect maybe 4, maybe half a dozen of these kinds of things. Instead, you find an incredible redundancy of these communication systems, and so, for example, when I was a graduate student many decades ago, there were basically 4 or 5 neurotransmitters, but now we're seeing neurotransmitters that are ranging up into the dozens, maybe even hundreds of different chemicals that can act as neurotransmitters. And so you have this tremendous amount of redundancy that's going on. On the other side, on the receiving side, let's just take one of these neurotransmitters, dopamine, which is a variation on norepinephrine. There's not just one receptor, there's dozens of them. There's an incredible redundancy of dopamine receptors. And so that's not really consistent with the notion that brains are computers. And what seems to be going on more, the metaphor that seems to describe that better is to treat the brain as a kind of an ecosystem. You have all these kinds of different agents there. They all do different things. They're all competing with one another or cooperating with one another to control flows of matter and energy. And so what I was proposing in this paper is that, if you want a coherent theory of brains, you're not going to find it in the cybernetic metaphor of what brains are. Where you're going to find it is going to be in the ecological metaphor for what brains are. And then you have a whole different set of criteria for judging what's right and what's wrong. If you're in the cybernetic world, then you want to focus on algorithms and what they do and how you can make them flexible. On the other hand, if you want to bring a more coherent theory of brains to it, then you really have to treat brains as an ecological type of metaphor. And then it becomes very easy to unify solid brains, liquid brains, fluid brains, and all the intermediates in between. And so that's what the basic argument is.
Brilliant. Thank you for that comprehensive explanation. And while on the topic of metaphors, I just wanted to add that the late Michael Roos was quite open to, not only open, I would say he was an advocate of the idea of the metaphor moving away from the machine metaphor that we use to the organism metaphor, which is an old idea. It's a really old idea. And it's an idea which is quite hard to adopt in a culture that's accepted the machine metaphor for such a long time.
This is tied into this is tied into a topic that we've explored before, namely, what is it that makes biology a distinct discipline from physics or chemistry? And the very uncomfortable conclusion for many biologists is that yes, life is distinctive, and therefore, biologists really have to be vitalists of a sort, and you have to think about things differently from the way physicists and chemists do. And a lot of my biology colleagues are very reluctant to make that leap.
Yeah, absolutely. And one of the reasons is that they were great thinkers of the 20th century who adopted the machine metaphor, and we made quite a lot of progress with that reductive metaphor. But also that, if we go back to very influential people at the beginning of the 20th century, like Schrodinger, in his What is Life, the famous lectures that he did, Noble points out that actually, the fundamental mistake that he made at that point about, what later developed into the crystal metaphor was this idea that, biology is different from the perspective that life, it starts with order to going to disorder when everything else is it doesn't have that type of stochastic or randomness in it. And obviously Noble argues that no, actually you do have that, and organisms are purposefully harnessing randomness, right? So the changing the metaphor has fantastic implications way beyond what you'd think, that how can a metaphor open up all these epistemic doors, but it actually can.
Yeah, I know, and this is well, I think this is the problem that sits in the heart at the heart of the mechanism vitalism controversy, which has been going on for decades, maybe even centuries, as you have pointed out, and the interesting thing about that is that the two sides really have no idea how to talk to one another. They are enclosed in a set of epistemic bubbles that doesn't provide a common language for them to talk to one another, and so this what to me is a very simple idea is that yes, life lives in a chemical and physical world. Laws of physics and chemistry do apply, but nevertheless, there's something else there that makes life distinctive from someone else, and or from all the other phenomena in the universe. And bridging that gap is very, very difficult, and of course, this is one of the marvelous things about social insects. Charles Darwin actually stubbed his intellectual toes on social insects, as you well know. And the marvelous thing about them is that they pose a fundamental challenge to really a lot of our notions about what biology is. In particular, it poses a real challenge to this notion that life is just mechanism, and as I said, the idea that it's just mechanism still is very strong in neurobiology and in robotics and artificial intelligence and those kinds of things. And it's very difficult to get people to, step out of that epistemic bubble. But nevertheless, I don't see how you can make progress on either side without it. And just to give you and I'm really speculating off the top of my head here, but if you look at artificial intelligence, everyone is all excited about artificial intelligence. It's going to take over the world, and these kinds of things. And I've looked at things like Chat GPT, and there are various kinds of other artificial intelligence apps that can do things like compose music or compose poetry, and those kinds of things. And they're all pretty boring. The outputs are pretty boring. They're pretty dull and seem kind of derivative, and and this is the outcome of the computational metaphor, the cybernetic metaphor of what intelligence is. And if you look at where intelligence comes from, we don't actually know how it gets there, but we know enough about intelligence in our own selves to realize that okay, there's some elements like large language models, for example. You look at examples, you build coherent things, narratives or things like that from basically what everyone else has done and put up on the web. But there's still this spark of creativity and innovation that you get from actual human beings thinking about things, as opposed to an artificial intelligence sort of thing. And artificial intelligence models are not really creative. They have a simulacrum of creativity, mainly because they're drawing from the creativity of everyone else. But you still have this hard nugget of, and I'm using a kind of a mechanistic materialist metaphor here, but you have this hard nugget of creativity and intentionality and drive in human intelligence, and I would argue in intelligence appears in other kinds of contexts like social insects or slime molds or so forth, that arises de novo, and that's what makes us different. And the little joke that I often tell about this is, we all remember Watson, the machine that beat Ken Jennings in Jeopardy, and okay, Watson may have beat Ken Jennings, but did Watson want to beat Ken Jennings? Was Watson actually didn't, well, Ken Jennings wanted to win in a big way, and in a way that something like Watson is not capable of doing. And this is really the basic issue with intelligence and brains, and so where does it come from? And at that point, we have to put on our biologist hats, and that means we have to put on our vitalist hats, and a lot of people don't want to wear that hat.
Absolutely. And I love the way you've linked those concepts together in a quite a lucid way. And while you were speaking, I was looking up the reference to help the viewers if they want to look further into the organic metaphor and the mechanistic metaphor, and why one prevailed over the other from the time of the Greeks, and why Roos himself thought that the organic metaphor is a better way of looking at biology. So just before he passed away, a book was published by Florida University. This is Michael's last book, Charles Darwin, No Rebel, Great Revolutionary. And in this book, he has a detailed explanation of the metaphor discussion. And I was really delighted to see a preprint manuscript from Roos himself. So he sent it to myself and Dembski while we were working on something.
Mm-hmm.
So that's a fantastic history of the use of these metaphors and where the different camps are and how they actually developed over time. So the next question I want to ask you, this kind of Scott, there may be a little bit of an overlap with you covering this topic previously, but I think it's important in this context to mention it again. So it's on homeostasis. You mentioned the core concept of homeostasis as a foundation for your theory. How do you see homeostasis playing a role in the cognition action coupling of different types of brains?
Yeah. Let's take something that is a good example of what seems to be a computational problem, but is really a problem of homeostasis in a brain. And I just mentioned it in the paper. It's how the brain constructs a three-dimensional world from basically two-dimensional information, and the way that's has been done is to use something called a random dot stereogram. And basically what that is, in comic book pages when those things were still printed, there used to be a regular feature called the magic eye, and it would be this kind of bizarre looking array of pieces of images that if you stared at in just the right way, you would see something three-dimensional come out of it. You can actually do that more randomly by this random dot stereogram. And basically what it does is it generates, it's kind of like a QR code, only not quite, but it's an array of black dots on a white background. And it's, there you go. Thank you. Good job. And what it does is it presents two different images to the two different eyes, right? And so the left eye perceives a slightly different pattern of dots than the right eye does, right? And the neurobiology behind that random dot stereogram, well, if you look at one of these, you can you'll eventually see, say, a ball in 3D, for example, or some other shape or whatever that comes from that. But it's something that takes a while to be able to see. And various people have looked into the neurobiology of that. And there's a very interesting dynamic that goes on. What happens there is that when you first see the random dot stereogram, the image from the left eye goes into the brain adjacent to the image you're getting from the right eye, right? And so what you have this disagreement between adjacent parts of the brain for, well, what is it actually that I'm seeing? I'm filling in some agency there. And this sets off a great deal of, back and forth conversation between these different cells that are disagreeing with one another about what they're perceiving. And eventually, when the image does resolve in your consciousness as a 3D image, that activity quiets down. So what happens is you have this ongoing argument between these two groups of cells, and eventually they just come to a point where, all right, well, let's agree on it's this. And what emerges from that is a conscious perception of a 3D image from basically 2D information. Now, that's a lot of computation that's going on, if we believe the computational metaphor. But biologically, this interaction between nerve cells is very stressful. One of the things that we often don't think about, because we often don't encounter it, is that you can overexcite nerve cells, so that, and in fact, you can overexcite them to the point they die. And certain disorders like Parkinson's disease or ALS have their origins in this kind of anomalous overexcitation of certain groups of nerve cells, that to the point where they die. And this is where the origin of the disease is. Now, what seems to be happening here is that the resolution of the random dot stereogram is you're going from a perturbation to a resolution, basically, and that's being driven by the need for maintaining a particular level of nervous activity between different parts of the brain that aren't too stressful. And so this is a very classic kind of a homeostatic type of a system. And if you build beyond that and you look at other kinds of disorders, for example, I mentioned one, Parkinson's disease, various kinds of movement disorders, all the way up to things like schizophrenia, where the brain is unable to build a coherent conscious representation of the environment. This is the basis of what schizophrenia is. You see the same kinds of stress related injury and degradation to the brain in schizophrenia that the resolution of the random dot stereogram is set up to avoid. And so you can look at homeostasis as at the level of brains as a means of helping coordinate everything, keep everything, all the activity at a steady level, so that the whole system persists rather than is injured and is degraded over time. And this actually leads directly to this ecological metaphor of the brain that I mentioned earlier. If you come back to this redundancy of neurotransmitters and neurotransmitter receptors and whatnot in the brain, this is very reminiscent of what's been called an evolutionary arms race that you get. So you get an organism that's being preyed upon by another one, and then organism one, I'm going to hold it this fist right here, organism one responds to that with a countermeasure, which organism two responds with a countermeasure. And what you get is this kind of elaboration of an almost rococo kind of system. And so if you look at the organization of the brain, you find that it's not just nice nerve cells communicating with one another. What you find is brains organized into nuclei of cells that have the same neurotransmitter, which then send out axons to another group of cells, which might have a different neurotransmitters, and they send them back. They send feedbacks back, and that's a common feature of most brains. You have clusters of similar cells trying to control other clusters of different but similar cells themselves, and they fight back, try to regulate that. And so you have a kind of, war of all against all going on in the brain, a kind of chemical warfare going on of cells with one neurotransmitter trying to dominate the activity of cells with another kind of neurotransmitter, and they fight back with other kinds of control and so forth. And when that chemical warfare gets out of hand, then you end up with movement disorders like Parkinson's or cognitive disorders like schizophrenia, and those kinds of things. And the healthy brain actually is a kind of détente, if you will, between these warring factions of nerve cells, and so that I think is much more amenable to the biology of what brains are, but it also helps you extend that metaphor to understanding things like fluid brains of social insects. There are groups of insects that communicate with one another, that try to dominate the activities of others, and they themselves are controlled by other groups of insects that are trying to dominate them, and so forth. And somehow out of that, and no one really understands why, somehow out of that kind of mutual accommodation that comes about, you get a coherent system that behaves in a coherent way. In humans, of course, it's the absence of cognitive disorders or movement disorders. In social insects, it's the control of the environment within the nest itself that comes about by manipulating the external environment and by manipulating each other as well. And it seems to me that the ecological metaphor for brains is far more amenable to building a coherent theory of brains around this concept of homeostasis, extended homeostasis in this case. And as we said earlier, this leads us into some uncomfortable vitalist territory for most scientists. But nevertheless, here's this great problem out there, and I think there's room to actually make a lot of progress towards this problem of bridging the mechanism vitalism barrier.
Yeah. And just keying off your point there, Professor Scott, in your discussion with Piglucci, you referred to vitalism with a small v. So it's not exactly what the 19th century vitalism is. Could you just explain that distinction again?
Yeah, sure. For this notion that life is a purposeful phenomenon, this goes all the way back to the Socratics, and much of the history of biology through then, or since then rather, has been built around the basically Hippocratic idea that you have vital fluids that actually are balanced somehow for the healthy body. And so you have black bile versus yellow bile, heat versus cold, wet versus dry, and those kinds of things. And so these vital fluids, existence of vital fluids was dominant until really the 18th century, and in the 18th century, everyone really started to realize that, well, this is not quite adequate, because one of the things that happened was that you had a proliferation of vital fluids that supposedly controlled life, and so you went from 4 vital fluids to where, well, if you had something that the 4 vital fluids couldn't explain, you would just invent another vital fluid, and so you got this proliferation of different kinds of vital fluids that emerged as people's thinking, and that was not really a very satisfactory way. In the 17th century, for example, no, 18th century, I beg your pardon. In the 18th century, you began to see the emergence of a quasi or proto-scientific approach to health and medicine. You had a number of the medical schools at that time building different conceptions, or realizing that this vital fluid or this vital essence model didn't really explain very much. And so there was a move to figure out some other way to explain unique properties of life, that is vitalism. And so there was one individual in particular, Théophile Bourdieu. He was at the University of Montpellier in France. And interestingly, he had a different idea that was inspired by watching a swarm of honeybees. He said, "Oh gosh, these things behave a lot like organisms. They seem to behave or what's going on?" And he uh, basically concluded that, well, it can't be a vital fluid that's doing this, because you have a bunch of different organisms, in the swarm. You can't get exchange of vital fluid between them in the same way you get, vital fluids driving things within the individual bees, for example. And he said, well, no, we have to get away from this essential vitalist point of view, essential meaning essences and these kind of things. We have to think about it in a different way. And his metaphor was that, no, you get the coordination of different parts of an organism to form an organism type behavior by looking at patterns of negotiation and mutual accommodation between the individuals in the group. And out of that came a very different kind of vitalism that was called process vitalism. That is, the unique nature of living systems came from this pattern of negotiation and accommodation between all the different components of a group of agents, like bees in a swarm, for example. And he posed actually kind of a compelling metaphor for it himself. He called it the many little lives hypothesis for how you get the unique behavior of organisms compared to different kinds of physical, non-living sort of things. All right, and so uh, when people brand vitalists today as being kind of spooky or non-scientific or any of these kinds of things, they're really ignoring this fascinating history of vitalist thought. And they usually brand people who talk like I do, for example, as believing in magical essences and all these kinds of things. They're branding all vitalism as this essentialist vitalism, but in fact, there's a different way of thinking about it, namely this process vitalism. Process vitalism recognizes, for example, that life exists in a chemical and physical world. It's not immune from it, but that there's something else that helps them basically make living systems distinct from others. And the the most famous process vitalist, of course, was Claude Bernard himself. That's what motivated him. He was a vitalist. He's touted as being this great father of experimental medicine, very, and supposedly very materialistic by implication and so forth. And he was a very great scientist, but he was a vitalist, because his thinking was motivated very strongly by this emerging concept of process vitalism that had taken over at the end of the 18th century and permeated our thinking through the beginning of the 19th century. So, you know, the whole conception of vitalism as somehow not scientific comes from basically this very narrow and actually, I think, poorly informed conception of what vitalism is and its history, and the ways it's inspired some very good science.
Yeah, absolutely. And it's really important to know this history because, Bernard not only was an eminent philosopher alongside being a great biologist, he also inspired contemporary thinkers like Noble. I was reading Noble's 10 Principles of Systems Biology, and at the beginning he goes over his inspiration there.
Yeah.
I think what's also important here to know about the history is just like you can have process vitalism, which it doesn't need anything spooky. It can be accepted within a naturalistic framework.
Hmm.
Likewise, when we're speaking about Darwinism, often people confuse Darwinism with neo-Darwinism. But
Yeah.
as Michael says, Darwin would not have accepted that as his legacy. And in fact,
Hmm.
uh, in the debate with Dawkins, he says that Darwin was a Lamarckian and I'm a good Darwinian. So,
Oh yeah.
it's important. I think it's really important, Scott, to know these.
Yeah.
It's not just about the science that we're doing today, but historical trends where it traces
Hmm.
back to these particular concepts. Because it's
Yeah.
hard to, I mean, biology, I think, is one of those sciences where it's very hard to separate the intellectual development of an idea from the science itself because of the
Yeah.
thread and the implications that it actually has.
Yeah. Yeah. I would just add to that, the whole process vitalism idea does rely on something that is very difficult to get into in a purely mechanistic way, which is that process vitalism, this concept of mutual negotiation and accommodation of the many little lives, however you want to define that, actually depends upon these systems being cognitive and intentional systems, and that's the philosophical nugget that is very hard to crack, and very difficult for a lot of people on the mechanistic side to wrap their heads around.
Yeah. Um, just sorry for another slight divergence, but this was a question I was going to ask you because it is linked to what you're saying. During your discussion with Piglucci, um, there were some things which he said which there wasn't enough time to go back and forth on. But one of the things I remember him saying is um, a colony is not an organism, right? And that's obviously very much contrary to what you're saying in terms of your paper. So, I mean, how would you summarize why we can think of a group of organisms, a particular swarm, as one organism?
In part, this problem derives from our not really knowing what an organism is. We tend to be very object oriented in our own perception of things, and so we tend to look at organisms as discrete bodies, right? I'm in a different body than you are. The tree outside my window is in a different body than I am, and these kinds of things. And so we tend, by virtue of maybe being hardwired that way, there's that computational metaphor again, that organisms are discrete objects, right? And if you look at the diversity of living things out there, uh, you know, there are all kinds of different ways of doing it, and the obvious or conceiving of an organism. And so this is where the superorganism concept comes in, of social insects. What unites the behavior of what we conventionally perceive as an organism with something like a superorganism is that they have vague similarities in the ways they behave. And so we are actually a collection of organisms ourselves. We're basically a giant a living continent, if you will, that is populated by all kinds of different types of cells,
Yeah,
some of whom or some of which, I suppose I should say, are derived from the zygote that came from the fertilization of an egg and with sperm. But then there's all these other kinds of things that exist on us. And yet there are certain attributes of ourselves and any organism that brand us as an organism. So, among them that we persist in a particular form, that when challenged we behave in a coherent way. All the parts of our bodies behave in a coherent way. We seem to be purposeful. We seem to be intelligent, and all those kinds of things. And yet, our conventional definition of an organism, we actually are colonies of lots of different other subsidiary organisms, the cells that make us up. And when you see the same set of behaviors like coherence, acting together, resistance to perturbation in assemblages of organisms, as you get in a social insect colony, then that's where we would that's where the superorganism idea starts to take on some relevance. But you can't approach those things by looking at life as a group of objects. In other words, you can't really get to the concept of the organism from a reductionist standpoint. What you're looking at is similar behaviors at different levels of organization. Our cells are one, which themselves are kind of superorganisms as well. If you believe Lynn Margulis, for example, we are assemblages of coherent cells that interact in negotiation between the many little lives that make us up. Social insects are the same kind of set of organizations, and what unites all of these is this network of negotiation and accommodation that produces something coherent. And I would argue that there's basically no upper dividing line to the concept of the organism. And then, of course, we get to James Lovelock's notion of Gaia as an organism, which, as I said, makes absolute perfect sense to me. The outer boundaries of the organism concept really extend all the way to the biosphere. I don't see any dividing line that goes on there, and that really divides one organism from one organism at one scale from organisms at entirely different scales. It's all dependent upon this, mutual negotiation and mutual accommodation of many little lives in the service of a persistence. So
Yeah, absolutely. And this goes back to, I guess, Dupree has a fantastic take on this in terms of his process ontology and,
yeah,
things being simply a illusion from the perspective of with fixed
yeah.
boundaries and
Mhm.
the way that they actually formed. And it totally changes the perspective this perspective totally changes the sort of things that you can conclude about organisms. So this is a good segue into our next question about emergent behavior. So in your paper, you discuss social organisms and emergent behaviors in fluid brains. Can you share examples of how these emergent behaviors manifest in social insects or human societies?
Um, well, let's see. The well, let's take some examples of emergent behavior, and you can tell me if I'm getting off the topic that you're thinking of, right? And so, if you look at brains, no matter how you define them, you have a couple of you have several different dimensions of how those brains act as cognitive systems, and I laid out four of them in the paper. One is that a cognitive system should represent what the external environment is. It should also be able to track changes in the external environment, right? And those are pretty conventional uh, concepts. But then, in addition to this, you have cognitive systems that can act as intentional systems, and also cognitive systems that can act as creative systems. Was that what you were thinking of? Or?
Yeah.
Yes. Okay. So, in in all those cases, you can build uh, a concept of a cognitive system that can actually serve as a platform for explaining all of those. And so, for example, representation. When I see something with my eyes, what it does is takes the input from those eyes and maps it onto a cognitive representation that exists in my occipital cortex and brain. And there's a predictable relationship between the stimuli that are presented to my eyes and the kind of cognitive representation that actually is constructed in the brain. And so representation should give a pretty good mapping of an environment really onto a cognitive representation of the environment. All right. Tracking is very similar. So if, I'm looking out at the tree out there, it's not moving around all that much. But if I take a look at my cat wandering around the tree, environment's changing, the sensory inputs are changing, and a good cognitive system should actually be able to track those changes pretty closely. And of course, when you're talking about the cat being a saber-toothed tiger or something like that, then it has real survival value to track them accurately. Where some of the other aspects of cognitive systems come in turns on the fact that cognitive systems are not only means of building cognitive maps in a nervous system or a brain or what have you. You actually have to, well, all of those being biological, they're coupled to engines, if you will, that can do work to change the environment. And when you're talking about social insects like termite colonies, for example, one of the big things that they do is they're big time constructors of the external environment, right? And in that case, you have the external environment. Well, I should say the external environment becoming a representation of the cognitive environment, if that makes any sense. And so, if, for example, you have a particular sensory input, then that is coupled to a body or a cell or some kind of enzyme system that can do work on the external environment to bring it into conformity with the cognitive representation of it. And when you start getting into that, then you start getting into all kinds of interesting implications. So for example, in the brain, if you have multiple inputs into the visual cortex, for example, the cognitive map in the visual cortex may not correspond perfectly to the sensory inputs. You see what I mean? So you may get it being influenced by sensory inputs from the auditory system or the smell system or taste or what have you. And what can happen then is you'll have a cognitive representation that is a little bit different from the sensory representation. And because the cognitive representation is built into a system that could do work on the external environment, it can actually bring the external environment into conformity with the cognitive representation of the environment. There are some diagrams in that paper that illustrate that. And then, you have, and so that's a form of intentionality, right? You're perceiving something, you're building a cognitive representation, and you're bringing the environment into conformity with something. That's kind of the nugget of what intentional behavior is. Yes, there we are. And it's not a far leap to build from there into creativity. I mean, sometimes, cognitive systems create entirely new cognitive worlds that are detached entirely from the sensory representation of it. And if you can do things like bring the external environment into conformity with that de novo cognitive map, That's the essence of creativity right there. And so when you're talking about these kinds of emergent behaviors, they're not difficult to explain conceptually, as long as you take a fairly broad view of what cognitive systems are and what they do, and you can derive from that very simply, emergent properties like intentionality, purposefulness, creativity, and those kinds of things. And I would treat those kinds of things as kind of emergent properties of these cognitive systems. Now, saying that is easy conceptually. Turning it into some kind of a coherent experimental proof of it, that's an entirely different thing. And in our conversations with Massimo Pigliucci, I was quite honest. We don't know how to do this yet, but we never will if we don't ask the question. And one of my issues with the whole neo-Darwinian idea is that they're even resistant to asking the questions.
Yeah, yeah, absolutely. You're absolutely right about that. But it's not only resistant to asking those questions, it's also um, giving this, painting this veneer of coherence that neo-Darwinism has answers to these things when they clearly don't have the conceptual tools for that.
I think so. Yeah. Yeah.
And even harder than the evidence actually is sometimes making the in interdisciplinary connections between these things. So the next
Yes.
question is about the implications of your paper for other fields. So how does your theory engage with existing research in neuroscience, psychology, or even artificial intelligence?
Well, I mean, I'm a guy who's interested in social insects and evolution, so I'm not quite sure I'm the best person to answer that. I can say that in the collaborations that I've had with people who are into the robotics uh, and swarm intelligence kind of idea, there are some real parallels there, and there are some divergences as well. So for example, the name of the author escapes me right now, but the point's been made that when you're talking about intelligence, really all intelligence is a social phenomenon. In brains, for example, it arises from social interactions between different types of nerve cells. No clue how intelligence comes from that, but that seems to be the case there. Just as swarm intelligence arises as a social phenomenon as well. So I think that's one parallel, but again, it's the same thing as the problem with consciousness. We have no idea what it is. We have no idea where it comes from. We can talk about different kinds of correlates of consciousness, but we really have no idea what consciousness is. And I would argue that we don't have any idea what intelligence is either. In the case of artificial intelligence, one of the things that's missing from there are a couple of things actually. One is a willingness to admit, and maybe we're getting into spooky phenomena here on our own part, things like intentionality and creativity and those kinds of things from our discussions of what artificial intelligence is. As I said, it's very much a computational phenomenon. But Barry Smith and Jobst Landgrebe, I think his name is, they've made the point that, well, artificial intelligence can't possibly mimic general intelligence that we have, in part because there's no motivation there. It's just data mining of what other people have done. And also, it doesn't really seem to account for the very fluid nature of social interactions between people that intelligence works on. And instead of starting from a single set of boundary conditions, what you end up with general intelligence is this ongoing resetting of what the boundary conditions might be, and this results from the kinds of conversations that go on between agents, in our case, different human beings, and those kinds of agents. It's a very dynamic phenomenon. It's driven by purposefulness. It's driven by desire, and that kind of thing just doesn't enter into artificial intelligence except by proxy of the programmer's own general intelligence, which so it's more of a simulacrum of intelligence rather than intelligence itself. I think that when you come to try to explain intelligence and other kinds of conscious phenomena like that, you cannot get away from the fact that these are biological phenomena, and if we believe what Claude Bernard said, ultimately phenomena of homeostasis and the unique nature of living things compared to everything else in the universe.
Yeah, thank you for that answer. The last question I want to ask you is about future research. So in terms of young scientists and researchers, what are the implications of your findings, and what further developments would you like to see in the field in the coming decades?
Well, I mean, obviously, I'd like to see more people agreeing with me, but it's part of the nature of the way we perpetuate science, that we're when we're students, we're necessarily embedded in a culture that has existed previous to us, and so these kinds of cultural phenomena are cultural means of transmission of a tradition. They're a very important part of what we do, and so change is necessarily going to be slow. The old trope that new ideas go through. Well, it's absolutely wrong to say, well, maybe it occurs in a few limited circumstances, but it's not really the general rule. To, oh well, we knew it all along. This is a process that takes probably a couple of generations to take place, and to be honest, that's probably going to be beyond my lifespan. Who knows? We can always hope, but nevertheless, it's going to be a long-term project. I am hopeful, among other things, that openness to these ideas is becoming more prevalent. The Third Way of Evolution group is one of them. I've really been heartened by its existence, and to realize that there are other people who think, at least not like I do, but in a similar kind of philosophical framework as I do. I think that there's a lot of potential to be exploring these issues in contexts other than organisms, and in particular other organisms besides humans. And again, I see glimmers of that arising here and there. And I see some interesting willingness to reach across boundaries. And so you mentioned a book that was a collaboration between, of all people, William Dembski and Michael Roos, and that speaks very highly to the open-mindedness and breadth of thought of both of those individuals. And of course, the hope is that will be a model for training future generations of scientists interested in these sorts of things.
Yeah, absolutely. And I believe the work that you're doing, and those of your colleagues at Third Way, is something which is going to facilitate a revolution in evolutionary biology, and it's something which should be supported culturally. And I'm really glad to be giving my platform to yourself and Shapiro and others. Mm-hmm. And I think what's important as well in terms of the way that we conduct ourselves is to speak to the other side, even if you totally disagree. I think there's not enough of that happening. So I'm looking forward to more dialogue from different perspectives. But also,
Me
one
too.
more thing I wanted to just add about the work that yourself and others at Third Way are working on, is that all of this is theologically neutral. You could come from any background. You could be a naturalist, a non-naturalist, a deist, a theist, or whoever. This isn't about, this is about keeping things quite. Darwin wouldn't pigeonhole pigeons, and we don't want to, as this was famously said about him, we wouldn't want to do the same thing where it's like, okay, because this person comes from this perspective, they have to subscribe to this reductive mechanistic
Yeah.
perspective, and this person has to accept holism, because
Mhm.
life is a process, and people have varying degrees of opinions, and it's not as
Yeah.
black and white as people paint it to be.
Yeah. It is theologically neutral. You're right, and one of the more disheartening um, points of resistance is to basically brand dissenters in this whole thing as somehow stealth creationists or looking to impose theocracy on education or things like this. This is a very destructive, reaction to dissent. Not just in evolutionary biology, but of course everywhere you see it. Everywhere
Yeah.
you see dissenters emerging from the status quo. You cannot treat them as somehow demon spawn. And even though I have my differences with the adherents of intelligent design theory, like Bill Dembski, you know, there's still interesting things to be learned from having honest conversations with them.
There is, and something I love uh, that Shapiro wrote about this particular topic was, um, by neo-Darwinists like Dawkins giving these categorical answers, that, okay, we've already worked it out. And this is something in his book, Evolution of View from the 21st Century. He actually speaks about a conference he attended where
Mhm.
Dawkins was making these sort of categorical statements. Shapiro believes, well, that's actually giving ammunition to the creationist or intelligent design proponents, as opposed
Uh,
to Shapiro, who actually, and I've said
yeah,
this to yourself, and I've said this previously as well, that if anything, then neo-Darwinists should look at the third way of evolution as being another maybe barrier to intelligent design, as opposed to a force for intelligent design.
yeah. I agree. I mean, the right answer is going to come from dialogue, open,
Absolutely.
honest dialogue.
Absolutely. So thank you so much, Scott, for your time. I am, again, delighted to have you back on the channel. Any last message you want to give to the viewers before we end?
I'm delighted as well. I'm really grateful for having this platform to expound.
All right. Cheers. Thank you so much.
Okay, so